Good evening. Welcome to week 11 class of basic electric circuits. Today we'll be discussing some tutorial problems, sample problems. So the first question is, two elements P and Q are connected in series as shown in figure. If current I of t in the circuit is 0.5 cos 4t minus 30 degree, then which of the following set of element values is correct? Please go through the question. So we have a circuit containing two elements P and Q. Now the options for P are all resistors. So we can conclude that P is anyway a resistor and Q could be an inductor or a capacitor. So the voltage in the circuit as well as current in the circuit are given. So the voltage is given by 24 cos 4t plus 30 degree volts and current is 0.5 cos 4t minus 30 degree amperes. So you have a circuit whose voltage is known and current is also known. Now let us represent it in phasor domain. While marking these phasors in the phasor domain, we have to fix the axis of phasors. As I have explained in previous classes, if you are taking your x-axis as sine, then cosine will lead sine by 90 degree. A cos signal is like this. This is 90 degree, whereas a sine wave is like this. So the cosine wave is 90 degree ahead of sine. So in the axis, quadrant axis, cos will be in the y-axis if you select sine in the x-axis. Keeping this in mind, in the given problem, anyway the voltage as well as current are given in cos. So you can choose the reference frame as cos. So I am choosing the reference frame which is my x-axis as cos. So your sine will come in the minus y-axis. So let us mark these phasors in the quadrant. This is my cosine domain which is a reference domain, that means 0 degree. So you have your current as well as voltage. Now V of t magnitude is 24 and angle is 30 degree from the reference. I have taken cos as the reference. So from cos 4t it is leading by 30 degree. So each of this quadrant has a frequency, it's a fixed frequency. So this quadrant which I have drawn has a frequency of 4 radian per second. So cos omega t will lie on the reference axis, whereas cos omega t plus 30 degree will be 30 degree ahead of cos axis. So this is my voltage. So the voltage can be represented as a phasor with magnitude 24 and angle 30 degree. Similarly, for current, the magnitude is 0.5 and the angle from the reference axis, which is the cos axis, is minus 30. So current will be 30 degree moving in the clockwise direction. So here is your current. So this is how you represent in the phasor domain. This is also 30 degree, that much ampere, that much volts. Now you know that your impedance is voltage by current. So you have 24 angle minus 30 degree divided by 0.5 angle minus 30 degree. There is no need of phasor representation in the given problem. Just for understanding purpose I have explained. So this comes out to be 24 plus j root 3 times 24. That means it has two components, which is r plus jx, where r is 24 and x is 24 root 3. If you observe the sign, you have two types of impedances. One is inductive and another is capacitive. So J could be R plus Jx, or Z could be R minus Jx. The sign will be negative in the case of a capacitive circuit, and the sign is positive for a inductive circuit. Because for an inductor, the inductive impedance is JXL, where XL is omega times L. For a capacitor, ZC or capacitive impedance is 1 by j omega C, or it is minus j by omega C, or it is minus j into XC, where XC is given by 1 by omega C. So the imaginary part of your impedance is negative. If the imaginary part of impedance is negative, then the circuit is capacitive. If it is positive, then the circuit is inductive. So in the given problem, you have positive sign. That means the circuit is inductive. So your element Q is an inductor. Anyway, P is already a resistor. So you know that the value of P is the real value. The impedance we obtained is 24 plus j 24 root 3, where the real part is the resistive part. So resistive part is nothing but the P, and its value is 24 ohms. Now Q is an inductor whose inductive impedance, which is XL, is given by 24 root 3. Now XL is nothing but L times omega, and omega is given in the problem we have already drawn, which is 4 radian per second. So omega is 4, that means 24 root 3 is 4 times L, or L is 24 root 3 by 4, which comes out to be 10.39 Henry, which you can approximate as 10.4 Henry. So your P is 24 and Q is 10.4 Henry. So the answer is option A. So the important takeaway of this problem is that the impedance will have real part and imaginary part. The real part corresponds to the resistance and the imaginary part corresponds to either inductor or capacitance. If it is positive, the circuit is inductive. If it is negative, the circuit is capacitive. Let us move on to the next problem. Please go through this problem. For the circuit shown in figure, the Thevenin voltage V Thevenin and impedance Z Thevenin across the terminal AB is. So we have given a circuit and we are asked to find the Thevenin equivalent voltage and Thevenin equivalent impedance. Let us find out what is Thevenin equivalent impedance first. Across whichever terminal you are asked to find the Thevenin equivalent circuit, first we should remove the components in between the terminals and open circuit it. But in the given problem, we are already given the open circuited circuit, so we are asked to find what is the Thevenin equivalent voltage as well as impedance across AB. While finding Thevenin equivalent impedance, we have to take away all the independent sources in the circuit. We have to replace it with its equivalent internal impedance. For a current source, whether alternating or constant, in the given problem it is alternating, the internal equivalent impedance is infinity. So you have to replace the current source with an open circuit. Whereas in the case of a voltage circuit, voltage source, for the case of a voltage source, you have to replace it with a short circuit. So, because the internal impedance of a voltage source is 0 and that of a current source is infinity. So, in the given problem, you have two current sources. In the given problem, you have two current sources. One is this and another is this. So, while finding Z Thevenin, you have to remove those current sources. While finding Thevenin equivalent impedance, you have to replace those current sources with an open circuit. Now we have to see what is the equivalent impedance seen across terminals A and B. So when you see across terminal A and B, since these terminals are open, they do not take part in the circuit. So when you draw from A and B, what you see is, you see a resistance 20 ohm that is connected to an inductor of 40 impedance and then a 20 J ohms inductor. That means it is a series RL circuit. So the impedance, Thevenin equivalent impedance is nothing but that which you see across AB. So ZTH is equal to 20 plus J40 plus J20, which is nothing but 20 plus J60 ohms. So you got the answer for Z Thevenin. So Z Thevenin is 20 plus J60. So it could be either option A or option C. Now let us see what is your Thevenin equivalent voltage. So Thevenin equivalent voltage, while finding it, we have to retain the circuit as it is. We should not remove the independent or sources and replace it with its equivalent circuit. That should not be done. You have to maintain the circuit as it is and see what is the open circuit voltage. So Thevenin voltage is nothing but the open circuit voltage seen across the terminals, across whom you have to find the Thevenin equivalent circuit. So that means you have to retain the circuit as it is. And you have to find the voltage, this voltage. This is V Thevenin, which is a phasor. Since it is an open circuit, you can observe that this current cannot go through this path because it is open. So they will definitely flow through the parallel branches. That means three angle 90 will flow through J40 and 2 angle 90 will flow through J20 because the current cannot enter the open path. So V Thevenin, these terminals are already given VA and B. So I can write the node voltages as VA and VB. So V Thevenin phasor is nothing but the difference in this node voltages, which is VA and VB. Now, if I give this node as C, you observe that VA is same as VC because there is no current through 20 ohm. That means there is no voltage drop across 20 ohm. So VA will be same as the term potential at node C. Now, what is the potential at node C? I have the liberty to choose any one node as the ground reference node whose voltage is 0 volt. Now, the voltage at terminal C is nothing but the voltage across 40 ohm inductor, which is nothing but the current flowing through it times the impedance, which is J40. Now observe that the current is going from top to bottom. That means if you take the inductor J40, the current is going this way, 3 angle 90. If current flows, wherever point the current enters the inductor, that will have higher polarity. So this is your VC. If the current direction was reverse, if 3 angle 90 was going like this across J40, then your VC is nothing but minus 3 angle 90 times J40. This is another case, but in this case the current direction and the polarity of VC are same. So VC can directly write as voltage across 40 ohm, J40 ohm, which is 3 angle 90 times 40 J40, which comes out to be minus 120 volts, which is your VC. Now the next is VB. Now where is VB? VB is here. Now the direction of current through J20 ohm. If you draw J20 ohm, the direction of current is downwards and its value is 2 angle 90. So the positive polarity across J20 comes here, which is same as your VB. So VB is same as voltage drop across J20 ohm, which is nothing but 2 angle 90 times J20, which comes out to be minus 40 volts. So VC is nothing but VA, which you have already seen before. So your V Thevenin is nothing but VA minus VB. VA is minus 120 and VB is minus 40. So it is minus 120 minus 40, which comes out to be minus 120 plus 40 or minus 80 volts. So the answer is option C. We'll move on to the next problem. In the circuit shown below, if V1 is equal to sin t and V2 is 2 sin t plus 60 degree, then the phasor diagram for the given circuit will be. You have a resistor and a capacitor connected across two voltage sources, V1 and V2. Now if V1 and V2 are there and if we ground this point, then at this node the potential is V1 and at this node it is V2. And essentially the potential across the resistor and capacitor is V1 minus V2. Let V be V1 minus V2. V1 is given as sin t. So in the time domain, V1 is 1 sin t and V2 is 2 sin t plus 60 degree, that much volts. So here both are expressed in terms of sine. So let us take the sine as the reference quadrant or reference phasor. So this is my sine and this is my reference phasor. So V1 of t lies in the reference frame and V2 of t lies 60 degree ahead. Plus 60 means you have to move in the anti-clockwise direction. So V2 is somewhere here. Both are phasors and this angle is 60 degree. So if I write the phasor representation, V1 will be 1 angle 0, where 1 is its magnitude and 0 is its reference. It lies on the reference axis. Now V2 is its magnitude, which is 2, angle 60 degree from the reference axis, that much volts. Therefore, V, which is V1 minus V2, will be 1 angle 0 minus 2 angle 60 degree. Now this comes out to be minus root 3 j or angle 90 degree. Now you have a series circuit of R and C, or just series circuit of two impedances across which a voltage of V is applied, and this is say P and this is element Q. The impedance is ZP and ZQ, or let us, so the voltage across ZP is VP and that across ZQ is VQ. Now according to voltage division rule, the voltage across impedance P is a fraction of the total voltage V, and that fraction is directly proportional to the impedance of P divided by the total impedance, which is since it is a series circuit, which is ZP plus ZQ. Similarly, the voltage across Q, which is VQ, is V times ZQ divided by ZP plus ZQ. Following the voltage division rule in the circuit which we are interested in, you have a resistor and a capacitor in series. This is R and this is ZC. And you have a voltage V applied across it. And the voltage across your ZC is VC. So VC is given by V times ZC divided by R plus ZC. Now ZC, these are all phasors and impedance is vector. ZC is the impedance of capacitor which is given by 1 by j omega c. Anyway, it is already given in the problem as minus 2j. And your value of R is 1 ohm. Now V we obtained before, which is V1 minus V2, which is root 3 angle 90 degree. It is minus root 3 angle 90. So substituting all these values in the equation of VC, we will get VC as minus root 3 angle 90 degree times minus 2j divided by 1 plus minus 2j. J is nothing but 1 angle 90. So if you substitute this in your calculator, you will get VC as 1.54 angle minus 116.56 degree volts. Now let us represent this in the phasor quadrant. So you have your V1 in the reference V1. V2 is 60 degree ahead of V1. Now VC is from the reference frame 116 degree lagging, means you have to move in the clockwise direction 116 degree. So 116 degree lies somewhere here, which is your VC. So if you are writing VC in terms of time domain, your VC of t will be 1.54 cos t minus 116.56 degree, that much volts. Because my reference, I am measuring 116.56 from your cosine axis. Sorry, it is sine axis. The reference axis is sine. So this is sine axis and this is also sine. So this full angle is 116.56 degree. Now in the options given, what we got is V1, V2, VC. Now V1, V2, anyway it is not option C because V2 is lagging V1. So it's either A, B or D, but VC is also lagging V1. So the option B is correct, but there is a small mistake in B. It is 180 degree apart, but in real case it is not 180 degree. It is bit more than 180 degree. So the options are actually wrong. This is the answer. The difference between V1 and V2, which is your V, we obtained it as minus root 3 angle 90, or it is root 3 angle minus 90. So your V is here. So finally when you draw, your V1 is here, V2 is 60 degree ahead of V1. Difference between them is here and your VC is here. This angle is 116 minus 90, which is around 26.56 degree. And this is 90 degree. So this is the correct answer. Let us move on to the next problem. What is the magnitude and phase or plot of voltage across the inductor in the circuit shown below? So you have a series RLC circuit. Across which a voltage of Vs is applied. As explained before, voltage division rule, the voltage across the inductor is a fraction of the total voltage Vs. So which is Vs times the impedance across L, which is ZL, divided by the equivalent impedance. Since it is a series circuit, the equivalent impedance is R1 plus ZC plus ZL, where R1 is the resistance, ZC is the impedance of the capacitor, which is given by 1 by j omega c. ZL is the impedance across the inductor, impedance of the inductor, which is j omega L. Substituting these values, VL comes out to be Vs times ZL, which is j omega L, divided by R1 plus ZC, which is 1 by j omega C plus j omega L, which can be written as Vs j omega L divided by R1 plus j times omega L minus 1 by omega c. Because 1 by j omega c, both sides you can multiply with j, so it becomes j by omega c into 1 by j square. Now j square is nothing but root 1 minus 1 whole square, which comes out to be minus 1. So this becomes minus j by omega c. That is 1 by j omega c is nothing but minus j by omega c. So it becomes, if you take j outside, it becomes minus 1 by omega c. So you have a phasor VL, which is which is Vs vector phasor times j omega L divided by R1 plus j times omega L minus 1 by omega c. Now this has both magnitude and phasor. The magnitude, which is magnitude of VL, is given by, the numerator magnitude is omega L, Vs, magnitude of Vs times omega L, and the denominator magnitude is under root R1 square plus omega L minus 1 by omega c the whole square. For a phasor or a vector of the form a plus jb, the magnitude is a square plus b square. So in the numerator, the real part is 0. So it is 0 plus j Vs omega L, or Vs if you take outside, Vs into j omega L. Magnitude of Vs is magnitude of Vs times under root 0 square plus omega L square, which is nothing but omega L itself. That is how the numerator magnitude is magnitude of Vs times omega L, and denominator magnitude is under root R1 square plus omega L minus 1 by omega c the whole square. Now the angle. So if you have a phasor x vector of the form vector a by vector b, then the angle of x is angle of A minus angle of B. Now the numerator is Vs magnitude j omega L. Now Vs you can take it as reference. That means Vs is nothing but Vs angle 0. So the angle of Vs is 0. Also this is for division. For multiplication, if x is of the form A times B, then angle of x is angle of A plus angle of B. So you have the numerator vector Vs j omega L. Vs is nothing but Vs angle 0 j omega L. So this is of the form two vectors. One is Vs angle 0, another is omega L. J is nothing but 90 degree. So the product of this will have an angle of 0 plus 90, which is nothing but 90 degree. So if you want to write the angle of the vector VL, it is nothing but angle of numerator minus angle of denominator. Now angle of numerator we got as 90 degree. Now what is the angle of denominator? Now the denominator is R1 plus j omega L minus 1 by omega C. This is of the form A plus JB. So you have the real part R and the imaginary part omega L minus 1 by omega C. We are assuming that it is a inductive dominant circuit. So your Z lies here. Now this angle is your angle of Z because R is in along with the reference axis. So if you want to write Z will be magnitude of Z angle theta. So the theta is nothing but, if you want to write tan theta, it is opposite side by adjacent side, which is say y and this is x. So it is tan theta is y by x. Now y is nothing but omega L minus 1 by omega C. X is nothing but R. So the angle of impedance is theta, which is tan inverse omega L minus 1 by omega C, the whole divided by R, which is nothing but your angle of denominator. So your angle of VL vector now became angle of numerator, which is 90 degree, minus angle of denominator, which is tan inverse omega L minus 1 by omega C divided by R. So let us write down the magnitude and phase. So magnitude V is omega L divided by R1 square plus omega L minus 1 by omega C the whole square under root, and the phase is 90 degree minus tan inverse omega L minus 1 by omega C the whole by R1. Now you have to plot the magnitude as well as the phase with respect to frequency. Frequency is nothing but omega. So you want what is your magnitude with respect to omega and what is your phase. With respect to omega. For that you have to vary your omega from 0 to infinity. So let us see the end points, which is easy to analyze. So starting with at omega equal to 0. That means you have to substitute omega as 0 radian per second. So the magnitude at omega equal to 0 is magnitude Vs times 0 times L divided by under root r1 square plus 0 times L minus 1 by 0 times C the whole square. Now the numerator is 0. The denominator is r1 square plus 0 minus 1 by 0 the whole square. Now 1 by 0 is infinity. So when you replace 1 by 0 with infinity, your magnitude now becomes 0 by under root r1 square plus 0 minus infinity the whole square. Now if infinity is there in the denominator, the other terms doesn't matter. So it is 0 by infinity itself. Infinity square is again infinity. Now this is nothing but zero into 1 by infinity. Now what is 1 by infinity? Again 0. So this is 0 times 0 or 0. So the magnitude at omega equal to 0 is 0. Now let us go to the options. Out of these options, which option has magnitude 0 at 0? Option C and D. So you can eliminate option A and B from the first observation itself. Now let us see what is the value of phase at 0 radian per second. So for option C it is 180 and option D it is 90. So if you solve for the phase at omega equal to 0, you will get the equation or the solution. So let us see what is the phase at omega equal to 0. Now at omega equal to 0, the phase you have to substitute omega as 0. So it is 90 degree minus tan inverse 0 times L minus 1 by 0 times C the whole divided by Rm. It is nothing but 90 degree minus tan inverse 0 into L is 0 minus 1 by 0 into C is 0 divided by R1. As I explained before, 1 by 0 is nothing but infinity. So it is 90 degree minus tan inverse 0 minus infinity by R1, or this is nothing but 90 degree minus tan inverse minus infinity, because R1 is very small when compared to infinity, so it doesn't matter if you divide it by R1 or multiply it by R1. Now if you draw the graph of tangent function tan theta with respect to theta, it lies between plus 90 and minus 90 like this. Similarly, if it repeats, if this is 90 plus 180, 270, it will also go like this. So the tangent function, the smallest interval, which is between minus 90 and 90, it approaches infinity as the angle theta tends to 90 degree, and it approaches minus infinity when the angle theta approaches minus 90. That means if theta approaches 90 degree, tan theta approaches infinity. Similarly, if theta approaches minus 90 degree, tan theta approaches minus infinity. So in the given problem, it is 90 degree minus tan inverse minus infinity. So when does tan theta approaches minus infinity? When theta is minus 90. So this angle is minus 90. So this is nothing but 90 degree plus 90 degree, which is 180 degree. So your phase at theta or omega equal to 0 radian per second is 180 degree. So from option C and D, option C only, it reaches 180 degree. So the correct answer is option C. Let us also write for what will be the values when omega approaches infinity. Please try doing it your own. Let us discuss what will happen. You have your magnitude and phase. Please try to solve what happens when, for magnitude and phase, when omega tends to infinity. So let us rewrite the magnitude as Vs omega L divided by R1 square plus, I'm taking omega square outside, so this becomes L minus 1 by omega square C, the whole square under root. So I can take VSL, omega in the numerator and omega in the denominator. So this becomes R1 by omega the whole square plus L minus 1 by omega square C the whole square. So I can cancel out omega, so this becomes VSL divided by R1 by omega the whole square plus L minus 1 by omega square C the whole square under root. So this is your magnitude. Now as omega tends to infinity, I can replace omega with infinity. So this becomes R1 by infinity, R1 by omega is infinity square plus L minus 1 by infinity square C square under root. Now 1 by infinity is 0. So the magnitude becomes VSL divided by R1 times 0 square plus L minus 1 by infinity 0 means 1 by infinity square is also 0. So this becomes 0 by C the whole square under root. Now you know that VSL divided by this is 0 plus L minus 0 the whole square under root. So this becomes nothing but VSL divided by L, which is VS. VS is nothing but the magnitude of VS vector. So that means your magnitude is a constant and is same as the supply voltage at omega equal to infinity. Now let us see for your phase. Now phase as omega tends to infinity is 90 degree minus tan inverse infinity times L minus 1 by infinity times C divided by R1. So this is tan inverse or 90 degree minus tan inverse. Infinity times L is infinity. 1 by infinity is 0 by C the whole by R1. That much tan inverse. Now this is 90 degree minus tan inverse. Infinity minus 0 by C is again 0 by R1, or this is tan inverse. Infinity by R1 is again infinity. So this is your phase of voltage across inductor at omega tending to infinity. Now tan inverse of infinity, if you see the tan curve, 90 degree and minus 90 degree, this is theta and this is tan theta. As theta tends to 90, tan theta tends to infinity. That means tan inverse of infinity is nothing but 90 degree. So this becomes 90 degree minus 90 degree or 0 degree, which is as omega tends to infinity the phase. So we got the magnitude as a constant and phase as 0. Let us see whether it is obeying our option C. So for option C, as omega tends to infinity, your magnitude is a constant and phase is 0 degree. So that verifies our answer. So our option is C is correct. That's all for today's class. Thank you.